Yeah, hello everyone. Today we are going to discuss about Green's theorem and its application. So in the examination point of view, and this is a very important theorem. Okay. So Green's theorem. In the examination, they will ask state and prove the Green's theorem and its applications. Okay. So where we are using the Green's theorem, so how we can find the area of the surface, then volume of the surface, that thing, everything we are using by the Green's theorem. Okay. So let's see the here Green's theorem. So what is the Green's theorem means? See, A be a closed region in XY plane bounded by a simple closed curve. Okay. And the functions m comma n. So m comma n are is functions of x comma y, and it is continuous function have the continuous partial derivation. So then the integration of m dx plus n dy equal to double integration of dou n by dou x minus dou m by dou y equal to dx dy. Okay. So this is the Green's theorem statement. Okay. Now let's. So this is the proof, and in the examination also they will ask the proof also. Now, so this is the region. So this is a region. So this is the surface. So this is a region. So it is bounded by x equal to a and x equal to b and y equal to c into y equal to d. So this is the easy here is there. So okay. Now this is in between of a comma b and this is c comma d. Okay. So here we are assume the two curves. So one is C1 and this spot is C1 and this is C2. So let C1, C2 is that AEB. So here this AEB is there, no? So this AEB is C1. Okay. So this AFB is a C2. Okay. So this is y equal to F1 of x and y equal to F2 of x, that is a C2 curve. Okay. Now first let us see here the double integration dou m by dou y dx dy. So x is bounded by the limits of a to b and y equal to f1x and f2x and dou m by dou x dx dy. So initially first we are doing the integration with y. So that is become we are getting m x1 comma y and we are applying to the limits. So in place of y we have to substitute f2 and in place of y again we have to substitute f1, f2 and f1. Okay. So at the end this mx2 f2x dx minus mx fxn dx. So at the end of, so just we are changing the limits. Here a to b is there, no? So I'm changing that b to a and I'm putting the minus here. See, observe one thing here. Here a to b is there. So I'm writing changing to minus b to a. Okay. And I'm putting the minus symbol is here. So if you are taking the minus common, so this is m x1 comma y dx and b2 is a curve that indicated the curve C2 and similarly a to b is the indicated that C1. So finally if you are taking the minus is common, then integration of m into dx. Okay. So this is that first equation. Next similarly when you are taking that x equal to g1 of y and x equal to g2 of y, c1, c2 is that fab and ebf. Okay. Now we have to do the integration with respect to x. So Now in place of x, we have to substitute the g2 of y and next g1 of y. Next, the limits are c2d and c2d, no? C2d, C2d. So here observe one thing. So here d is a lower limit and c is upper limit. But we are changing the limit, so minus will become, that minus will become plus here. So d2c and g of y dy. So it's completely, that we can write, it's represented the curve C2 and this is represented the curve C1. So finally we are getting integration of n into dy c. So from 192, so 192, then we are getting, if we are adding this to, that integration of m dx plus n dy equal to the double integration of dou n by dou x minus dou n by dou y equal to dx dy. So this is the Green's theorem. Okay. So using the Green's theorem, so we need to solve some problems are here. See. Okay. So verify the Green's theorem in the plane for the function, and where C is the boundary of the square, here the curve is a square with the boundary condition that the vertices 0, 0, 2, 0, 2, 2 and 0, 2. Okay. Now let's see here. So by Green's theorem, so mdx plus ndy, so dou n by dou x minus dou m by dou x equal to dx dy. So from here we can find that this is a m, and m equal to what is that, x square minus xy cube. And what is the n? Y square minus 2xy. Now come to that RHS part. So what is that? M dx dou n by dou x minus dou m by dou y. So now we have to do the partial derivation with respect to x. Then we are getting, what is that? This is become 0 and minus 2xy, that we are getting minus 2y. Next, minus dou m by dou y. So this is a m, no? Now we have to do this partial derivation with respect to y. So when you are doing the partial derivation with respect to y, so that is become 3x y square minus 3x y square. So already here minus is there, no? So that's become 3x y square and dx dy. Okay. Now first we have to do the integration with respect to y. So integration with respect to y. So that is become minus 2y square by 2 and 3x y cube by 3. Okay. Now apply the limit 0 to 2. Okay. Now this is x equal to 0 to 2. Okay. Then we are getting minus 4 plus 8x into dx. So again we have to do the integration with respect to x, and we are getting, what is that, minus 4x plus 8x square by 2 and apply the limit 0 to 2. So at the end we are getting, what is that, 8. So 8 is the answer. So this is using that RHS part. Now let us see that LHS part. So what is the LHS part? So mdx plus ndy equal to 0. So what is the m? X square minus xy square into dx. And what is the y? Y square minus 2x dy. Okay. Now here, here that y equal to 0. Now you are observe that the curve in OA, x value is changing from 0 to 2. Let's see here. See, this is. So x is 0 to 2, but y is 0 to 0 only. So we can write y equal to 0. So you can substitute that, what is that? Y equal to 0. So if you are substituting that y equal to 0, then we are getting this thing, x square dx. So this is y equal 0, no? So this is completely is become 0, and only that thing is, what is that? X square into dx. So x square into dx, no? So x square into dx, then we have to do the integration, that is become x cube by 3 and apply the limit 0 to 2. So that is 8 by 3. Okay. Next, similarly in the AB. So in the AB also, that x equal to 2. So x is not changing. So x equal to, then dx is become 0. So but y is changing from, what is that? 0 to 2. So if you are substituting here x equal to 2, then we have to do the integration. This is become 0. So only the part will be there. This is y square minus 4y into dy. So y square integration is y cube by 3 and y integration is minus 4y square by 2, that is 0 to 2. That is 8 by 3 minus 8, that equal to 16 by 3. Okay, so this is 4. Next, along the BC, same procedure along the BC, the y value is not changing, no? So y equal to 2, then dy equal to 0. So along the BC, x is varies from 0 to 2. So x is 0 to 2, no? Then dy is 0. So this part is going to 0, this part. Okay. This one, y square minus 2x. Now we have to do the integration with dx. So when you are doing the integration with dx, x cube by 3 minus x 8x square by 2, and apply the limits. 2 to 0. Remember one thing here, 0 is the upper limit and 2 is a lower limit. Why? Because let's see here. So here, along here, see, 2 value is changing from 2 to 0. So 2 is a lower limit and 0 is a upper limit. Okay? Okay? So this thing. So if you're adding this all, next finally at the end, along the curve, CO. So y is varies from 0 to 2, x is 0. So x is 0, no? So dx is also become 0. So finally we are getting minus 8 by. Now if you are adding this all four things, this is the, okay? Then we are getting 8. So this is the 2 RHS part, 8. Then come to here, LHS part is also 8. So this is the things. So this is LHS equal to RHS. So here that figure is very important ma here. Here x is y is not changing. So we are checking y equal to 0. So y equal to 0, that implies dy equal to 0. Okay. Now here, let's see this part, this AB part. So x equal to not changing. So x equal to 2. So then dx is become, that is become 0. Okay. Next, here, BC. Y values are not changing. So y equal to 2. Then dy is become, what is that? 0. Next come to CO. CO, x values are not changing. So x equal to 0, then dx equal to become 0. So this is the things we have for this problem. Okay. We prove LHS and RHS. So we find out the LHS and we find out the RHS and both are equal. So we can say that. So it is. Now let's see here. So verify the Green's theorem for the plane xy plus y square into dx and x square into dy, where C is a closed curve, the region y equal to x and y equal to x square. Okay. So this is the curves y equal to x and y equal to x square. So from these two we can write what is that? X square equal to x. So x square equal to x now. So that's become x square. So from here we can write x square minus x equal to 0. So take x is common. So x minus 1 equal to 0. Then x equal to 0. So now first we are finding that suppose x equal 0 and we are getting y equal 0 and x equal to 1 and we are getting y equal to 1. Okay. So this is the things here. Now this is the point of intersection. No? So 0 comma 0, 1 comma 1. Okay. Now this is a graph. Y equal to x means that should be straight line and y equal to x square means this is. So the two curves are intersecting at the point 0 comma 0 and 1 comma 1. Okay. So y equal to x square. So y equal to x square. So when you are doing the differentiation, then y differentiation is dy and x square derivation is 2x into dx. And x is various from 0 to 1. Okay. Now integration of m dx plus n dy and 0 to 1 and m is xy plus y square into dx and n is x square into dy. So remember one thing, this totally we have to changing in x variable. Okay. So in x variables we are total changing. There are two variables x comma y, but we are changing into in x variables. Okay. Now this is changed, you know. Y equal in place of y, we have to substitute x square. Okay, that is x cube and this is x power of 4 dx and this is 2x cube into dx. Now we have to do that. After simplification we are getting 3x cube plus x power of 4 into dx. Now here we have to do the integration. So if we are doing the integration and we are getting 3x power of 4 by 4 plus x power of 5 by 5 and the limits are 0 to 1 and we are getting 19 by 20. Okay. Now along the straight line y equal to x. Let's see. So y equal to x, no? So dy equal to dx and x is varies from 1 to 0. So m dx plus n dy, this is 1 to 0. 0 is the upper limit and 1 is the lower limit. And xy plus y square into dx and x square into y. Okay, so this is the things. Now substitute same. Totally we are changing into in x. So y equal to x. If you are substituting that y equal to x, this is x into x become x square. And in place of y, we have to substitute x, that is become x square. So x square plus x square into dx and here x square into dx. So completely it's changed 3x square into dx. So that will become 3x cubed by 3 and 0 is upper limit and 1 is the lower limit. And that we are getting what is that? Minus 1. Okay. Now continuation. So again from 192. So if we are adding that is 19 by 20 minus 1. That is minus 1 by 20. Now let's see here that RHS part. Dou m by dou x minus dou m by dou y dx dy and the y is changing from x square to x. So x square is become upper limit. Sorry, x square is the lower limit and x is the upper limit. And x values are changing from 0 to 1. So that is dx dy. So dou by dou x of x square and dou by dou x of xy plus y square. So dou by dou x of x square is become 2x and dou by dou f of this is become what is it? X plus 2y dx dy. So after simplification and we are getting x minus 2y into dx dy. So initially first we have to do that integration with y. So when you are doing the integration with y, so that is become xy minus 2y squared by 2 and the limits are x to x square to x. So now first substitute the upper limit minus lower limit. So this is x square minus x square minus x cube minus x power of 4 into dx. X power of 4 minus x cube into dx and x power of 5 by 5 minus x power of 4 by 4. Now apply the limit 0 to 1. So that is minus 1 by 20. Okay. From 3 and 4 we have this is. So this is the RHS part and this is the LHS part. Okay, na? So this is the verify the Green's theorem. So here calculating the area bounded by the simple closed curve. So by the Green's theorem, so we have mdx plus ndy. So that equal to dou n by dou x minus dou n by dou y equal to dx dy. So taking the m equal to -1 and n equal to x, then we are getting dou m by dou y. So that end of the answer, just you should remember this thing. So a equal to 1 by 2, that integration of x dy minus y dx. So just you should remember this thing. So how we are getting this one? So we have this is simple closed curve. So simple closed curve, this is the thing. Okay. Now the find the area of the ellipse. So we know that area of the ellipse, this is x equal to a cos theta and y equal to b sin theta is the, that is a parametric equations. Okay. For the ellipse, the theta is varies from 0 to 2 pi. Okay. So x equal to a cos theta and y equal to b sin theta. Then dx equal to, that is become minus 8 sin theta d theta and dy equal to b cos theta d theta. So area is bounded by ellipse, that equal to a equal to 1 by 2 x dy minus y dx. So a cos theta into dy. Dy is what is that? B cos theta d theta minus y equal to b sin theta. So dx equal to minus a sin theta d theta. So that is a into b ab, cos into cos theta cos square theta, and here sin theta into sin theta minus sin square theta. But here already is minus is there, no? So that is become plus. So AB into cos square theta plus sin square theta. So AB into sin square theta. Now, so using the Green's theorems to find the area of the region is bounded by y equal to x and y equal to x power of minus 1 and x equal to 4 in the first chord. This is. So y equal to x power of minus 1. So that is nothing to what is that? Y equal to 1 by x. So this area, this region we need to find. Okay. Now first find the intersection of the points. So x equal to 4 and y equal to x power of minus 1. So, so here this is. So here write y equal to what is that? 1 by x. So from there we can write this is x equal to 4y now. So y equal to x power of minus 1. So from there we are getting x square equal to 4 and x equal to plus or minus 2. So but here in the first coordinate, this is all are place now. X coordinate is place and y is also place. So that's why we are taking that 2. So that a equal to 2 comma 1. Okay, now the point of intersection is y equal to x power of minus 1 and y equal to x is the p. Now then we are getting the p point. So p point is 1 comma 1. So a is 1, 2 comma 1 by 2. Okay, so this is the. Now come here. So we have x into dy minus y into dx. X into dy means dx by 4. So similarly, we are changing into all in one variable. So that's we are getting 0. Now come to along the AB. Same procedure. So x dy minus y dx. So then we are getting log 2. Okay, log 1 value is 0. Remember that thing. So 0 minus 1 by 2. Okay. Also b equal y equal to x and dy equal to dx and x is varies from 1 to 0. So this is x dy minus dx. So this is 0. From the these 3 points, so we can say that that is log 2. 0, 0, 0 plus log 2 plus 0. So this is log 2. So this is the Green's theorem. See here the one example is there. So evaluate 0 comma 0 to 2 comma 1. 10x power of 4 minus 2xy cube dx minus 3x square y square dy along the paths. So compare with these things. So this is the m and this is the n. Okay. So dou m by dou y. So dou m by dou y is minus 6xy square and dou n by dou x is minus 6xy square. So since dou m by dou y equal to dou n by dou y, no? So the integral is independent of path. So hence from the theory of differential equation, then we can say that generally exact differential equation. See, this is in that UG level in the first sem, in the differential equation in the second semester, we have that differential equation, exact differential equations. So when it is see the exact differential equation, let observe here these things. 10x power of 4 minus 2x square dx. This we can write what is that? D of 2x power of 5 minus x square into y cube. These things. So so integration and derivation going to okay. So integration derivation is cancelled. So here this is and integration and derivation is cancelled. So 2x power of 5 minus x square into y cube 0 comma 0 to 2 comma 1. So in place of x we have to substitute 2 and in place of 5 we have to substitute 1. So after that minus in place of x we have to substitute 0 and in place of 5 we have to substitute 0. So finally we are getting what is that? 64 minus 4. So that equal to 60. Okay. So this is the one things. Next, evaluate by the Green's theorem cos x into sin y minus xy into dx plus sin x into cos y into dy, where C is a circle, x square plus y square equal to 1. So this is the path. Okay. So by Green's theorem, m dx plus n dy equal 0 is nothing to what is that? Dou m by dou y. So this is the m dx plus n dy. So dou n by dou x. Dou n by dou x is sin x cos y minus dou m by dou y is cos x sin y into xy into dx dy. So this is cos x cos y. This derivation, sin x derivation is cos x and cos y is as it is we are writing. And dou by dou y means cos x is as it is and sin y derivation is cos x. And xy means x. So that is x into dx dy. So here using the polar coordinates. So when you are using the polar coordinates, that equation will be very easily to solve the question. So x into r cos theta and y equal to r sin theta. Then we have dx dy equal to r into dr d theta. So r cos theta, r into dr d theta. So first we have to do the integration with theta. That is cos theta integration is sin theta and apply the limits. Sin 2 pi minus sin pi. Sin 2 pi is 0. So completely that part is going to that 0. And this is the things. Let's see this one more. Same. So all are repeated as the Green's theorem only. So you should remember one thing. So in the Green's theorem, so that you should remember one thing. Green's theorem statement. Integration of m dx plus n dy equal to 0 is that double integration of dou n by dou x minus dou n by dou y into dx dy. So these both things you should remember. So all are the problem is the same thing. So here the figure is very important. So you have to draw the figure is that is very important. Let's see this one. So this is the figure. And let's see here the one more problem. X square 2xy dx x square plus 3 into dy, where C is the boundary of region bounded by y equal to x and y equal to x square. So this is y equal to x and y equal to x square, 0 comma 0 to 1 comma 1. So y equal to x square, no? So then dy equal to 2x dx and x is varies from 0 to 1. So completely we have to change in terms of x. So in place of y, we have to substitute x square, and in place of dy, we have to substitute 2x dx dx. So this is the things. So this is the things. Then we have to do the integration. X cube by 3 minus 2x power of 4, 2x power of 6 by 6 plus 6x square by 2 and apply the limit 0 to 1. So then we are getting 19 by 6. And similarly along the curve AO. So in this case, so that is 1 to 0 x square minus 2x square into dx plus x cube plus 3. Okay. Then all are we are changing into in terms of the dx. Let's see here there. So all we are changing into in terms of dx terms. So we are doing the integration with x. Then we are getting minus x cube by 3 plus x power of 4 by 4 plus 3x. So this 192. So this is that LHS part. Let's see, this is RHS part. First we are doing the integration with y. So this is RHS part. So RHS part value is 1 by 4. Therefore, that LHS part is also 1 by 4. Let's see, this is a very important problem. See this one. So all are only depending on only one formula. That is, so at the starting we discussed no the formula that mdx plus ndy equal to 0 equal to dou m by dou y, dou n by dou x minus dou m by dou y. So this is only we should there you go. That thing. So dou n by dou x minus dou m by dou y equal to dx dy. So this only formula. It's very important for you. So if you are remembering this formula, so in the examination, it's compulsory. This is very important. Okay, the proof and problem. So in the examination point, it is very important.